Okay, pause and copy all this. It'll take you a while, but pause and copy, pause and copy. Okay, the invertible matrix theorem. Um, so if one of these things is true, then they are all true. And if one of them is false, then they're all false. So let's talk about at least a part of the proof. So I believe I'm doing what's in the book. You can look at the book for the whole proof. So it's relatively straightforward to prove that these 5 things are related this way. So we'll say partial proof. I'll start by proving that A implies J. Okay, so let's look at this diagram here. So I'm telling you what I'm about to do. I'm going to prove that if A is true, then I can prove that J must be true. So if A is true, then J is true. And then I'll prove that if J is true, then D is true. And so on and so forth. And if you think about it, what that proves is that these 5 statements are equivalent. Okay, so if A is true, then D is true. If A is true, then B is true, and any combination you want. Anyways, A implies J. Why is that? Okay, what is A again? A is, sorry. So if something is invertible, then you have what's called a left inverse. Well, if you have an inverse, it's obvious that you have a left inverse, right? So if I assume that A is true, that means that A inverse exists. Okay, so what I'm going to do here is I'm going to assume that A is true and try to prove that J is true. Well, if A is true, then I know that A inverse exists. So C is equal to A inverse will work. So J is true. Okay, J implies D. Ooh, I got a little cross. I got a little typo here. I want to get rid of that little thingamabob. Where is it? Oh, there we go. J implies D. What is D again? D is only the trivial solution. Okay. So I'm going to assume J is true. Just J. I'm going to assume that there's a matrix C that does this for me. Well, so given so again, I'm going to assume J is true. So there's a matrix that does this for me. And I want to prove that D is true. I want to prove that this equation up here has only the trivial solution. So I'll say, oh, imagine I'm given this equation. And then you use C. I use C. And I multiply both sides by C. So x is 0 is the unique solution. Okay, so this equation here does indeed have just one solution. So D implies C. So what is C again? Well, N pivot positions. Okay, I assume D is true. So I assume that this guy here has only the trivial solution. This is the trivial solution. Now I want to prove that the matrix A has to have a pivot for every column. But this is immediate, right? A must have a pivot for every column. Because otherwise, AX equals 0 would have infinite solutions. Okay, so you can't have a free variable, right? If this is true. Okay, C implies B. Again, so given that I have a pivot for every column, why does a row reduce to the identity? Well, this is obvious, right? Just say pivot for every column implies, we'll say clearly that a row reduces to the identity. There's not much to say there. Because if you have a pivot for every column, you must have something like this with all zeros down here, and maybe you have whatever here. So if you have a pivot for every column, then in echelon form, you could certainly get here, right, as an echelon form. And then it's just a matter of creating zeros above the diagonal, which is exactly the identity. Identity. B implies A. This is done before. This is part of theorem, which theorem? 2.2. It's the algorithm. Oh, I lost it. Where is it? So we have it as theorem 7. So we'll just say, oh, we proved this before, so no sense in reinventing the wheel. Okay, so the other things can be proved The other equivalencies can be proven similarly. So it's all done in the book if you want to have a look. But I think I will leave it there for now.